and Wednesday it was so bad I was throwing up. I figured you'd rather I stay home than have to run to a trash can every 5 minutes while trying to lecture. It would not be fun for me or for you. So I posted a little 6-minute video in Canvas that kind of went over the tangent rule for sums and differences. Did we get a chance to watch that? I see at least 2 people nodding, so it was posted. Good. Okay. So what we're going to do today, yes. I didn't print copies. You were just handwriting because it was like the rule and then 2 examples. That's okay. So yeah, we're just adding on to that today. What I'd like to do is I'd like to start by verifying that trig identity for tangent for the sums. And then we'll do a couple of practice problems because I want to make sure that we know how to rationalize the fractions that you get from doing the tangent rule. I got the pass for you. Yeah. So let's go ahead and verify our tangent sum. Tan alpha plus beta. And I know what that equals. We should also know what that equals. Tan alpha plus tan beta over 1 minus tan alpha tan beta. You got that formula in Wednesday's video. We're going to show that that's what it equals. And we're going to start with the most basic definition of tangent. When we learned about tangent, what is tangent? What over what? Sine over cos. Perfect. Gold star. So this should be sine of alpha plus beta over cos of alpha plus beta. That's just the definition of tangent. Yeah. And we have some rules for sine and cosine. They come from looking at a difference between 2 points on the unit circle. We didn't do the derivation, but it's in the book. We know those formulas. So, formula for the sum inside of a sine. That was Monday's notes. Please check my work. I'm pretty sure that it's sine alpha times cosine beta plus sine beta times cosine alpha. Did I get that correct? And Liv's nodding. That's a good sign. Thank you, Liv. I'm old and my brain is fuzzy. It's nice to check. And then the bottom, we do the same thing. We replace cos with the formula for the sum of 2 angles in a cosine function. And I'm pretty sure that that starts off with cos cos. So cos alpha times cos beta, and then plus or minus for cosine. Minus, yeah, cosine has the weird one that changes sign, and then sine alpha, sine beta. Good. Perfect. And while that is technically correct, that is gross. There are 8 trig functions floating around. Pairs plus pair plus pair plus pair. Gross. I know what the goal looks like. I know the goal is 1 minus some stuff in the denominator. So my thought is, what can I divide everything by that will make the bottom left corner 1? Oh, again, why? And this only happens in 6th period. What is it about this class? Frowny face. Try that again. Okay, there we go. So what do I have to do to the bottom left? What can I divide by that'll turn that bottom left into 1? I want to divide 5 by something to turn it into a 1. 5 divided by what is 1? 5. 10 divided by what is 1? 10. 100 divided by 100 is 1. So if I want to turn this into 1, I should divide it by itself. Yeah, cos alpha, cos beta. So we're going to divide everything in that fraction, top and bottom, by cos alpha, cos beta. So let me zoom out a little bit. And we're doing the same thing to the top and bottom of the fraction, otherwise we change the fraction, and that's bad. Cos alpha, cos beta, we're going to divide by cos alpha, cos beta. And I'm going to ask you to bear with me. We're going to write this out, and it is going to be ugly for a second, but it makes a lot of sense when you see the ugly written out. Yeah? Okay, so big ugly fraction. Everything gets divided by cos alpha, cos beta. So that first term in the upper left, sine alpha times cos beta divided by cos alpha, cos beta. And I spy something that cancels. This is going to get pretty in a second. We're going to do the same thing to the upper right term. So upper right term is sine beta times cos alpha. We're dividing it by cos alpha, cos beta. And you probably see the pattern. Same thing to bottom left. The term that was there, cos alpha times cos beta, divided by cos alpha, cos beta. And then a minus. And then the last term in the bottom, sine alpha, sine beta, divided by cos alpha, cos beta. And now you know why we're doing it in class together, and I didn't assign it as like a homework problem, because that would be evil. I spy with my little eye some stuff that cancels. What's going to cancel? All the cosine betas. Yeah. I got a cosine beta here. Oh, not there, because that's cosine sine. Here it's cos alpha that cancels. Bottom left, what cancels? Everything. That's why we did that in the first place, right? We wanted this to become 1. Last fraction, what cancels? Nothing. I see head shaking no. Perfect. Good. Next thing I'm going to do is I'm going to pair up my sines and cosines, because I know as long as the angles in sine and cos are the same, sine over cos is tan. So in that first fraction, I see a sine alpha over a cos alpha. That's a tan alpha. Yeah. Second fraction, I see a sine beta over a cos beta. That's a tan beta. In the bottom, I see a sine alpha over cos alpha. That's a tan alpha. I also, directly next to it, see a sine beta cos beta, which is a tan beta. So all of those things we circled in blue, we are now going to replace with tangent, because sine over cos is tan. So that first fraction in the upper left becomes tan alpha plus, oops. Next one, I've got sine beta over cos beta, which is tan beta. On the bottom left, first fraction became a 1, followed by a minus, and the second fraction has 2 tangents. first circle is tan alpha. Second circle is tan beta. And I would bet my money for the week that that is the formula that they gave you in the video on Wednesday. Tan alpha plus beta is tan alpha plus tan beta over 1 minus tan alpha tan beta. Minus, sorry. So what happens if you do another division? So if we divided this whole thing by tan alpha, you get a 1 here, but then you'd have a ratio of tans that don't reduce, because it would be tan beta over tan alpha. So you'd be introducing fractions where we don't want extra fractions. Yeah, that was a good question. And no, this is as pretty as it'll get. It didn't have to be this. We could have, instead of dividing by cos, cos, we could have divided by sine, sine, and we would have ended up with a bunch of cotangents instead of a bunch of tangents, coses over sines. So there is a way to rewrite this with cotan instead of tan. The reason we go tan is sin, cos, tan are our primary trig functions, and then their inverse buddies are less commonly used. Yeah, no, that was a good question. Sometimes that's as pretty as it gets. We know for the opposite function, the one that's alpha minus beta, the minus sign is in the numerator, the addition's in the denominator, the signs flip. So the sign on top of the fraction should match the operation that was inside the trig function. The sign on bottom should be the opposite. What I'd like to do is do some examples for the whole process, start to finish, for finding some exact values. Yeah. While I am clicking buttons, if you don't have your unit circle out, you should get it out, because we're going to need our unit circle to evaluate those tangents. So first example, we're going to find the exact value of tan of pi over 3 minus pi over 4. And typically this process involves 3 steps. First, we're going to use the addition or subtraction formula to rewrite this of tan alpha and tan beta. I'm going to separate those angles. Second, we're going to use the unit circle to find those values for tan alpha and tan beta. And then the third step is we need to use algebra to simplify the expression. As unlike sine and cos, these answers are going to start as ugly fractions. We need to make them pretty fractions. Yeah? My experience doing this is 9 times out of 10, students do pretty good finding tan alpha and tan beta, and they get the substitution step correct. It's that last step with simplifying that we get stuck on. So that's what I really want to focus on today. Yeah? Okay. So first step, use the sum or difference formula. This is a difference, which means I know it's going to be subtraction in the top and addition in the bottom. And I know that it's tan alpha, whoops, and our alpha is pi over 3 minus tan beta, which is pi over 4. In the bottom, it's 1 plus tan A times tan B. So 1 plus tan pi over 3 times tan pi over 4. Yeah, that's just taking those two angles, pi over 3, pi over 4, and plugging them in to the difference formula for tangent. My next step is I need to figure out what tangent of pi over 3 is, what tangent of pi over 4 is. And that's where the unit circle comes in, because they set exact value. Should not be using my calculator for this. I should be using my unit circle. Yeah? So let's grab a unit circle. Maybe not over the top of my writing. That would be helpful. Yay. And we're going to identify where we're sitting on the unit circle. So my first angle is pi over 3. Pi over 3 is right here. My coordinates are 1/2 and root 3 over 2. Second angle is pi over 4. Pi over 4 is right here. Coordinates are right here. And we need to remember something important. When we look at the unit circle, those points on the unit circle are cos, comma, sine. Cos, comma, sine. Cos, comma, sine. So when I go to build my tangent, sine is on top, y is on top, x is on bottom. Yeah. So let's do those really quick. We'll start with tan of pi over 3. What is the y coordinate at pi over 3? Perfect. Square root of 3 over 2. X coordinate at pi over 3 is 1/2. I happen to notice there's a half on top and a half on bottom. I know those halves are going to cancel. If fractions scare you, rewrite this using the reciprocal rule. I know that this is the numerator, root 3 over 2, times the reciprocal of the bottom. And the 2's cancel, which should usually happen because all of those fractions are over 2. And I'm left with root 3 over 1, which is just root 3. That makes me happy. That wasn't so bad. We repeat for tan of pi over 4. Y coordinate is what? Root 2 over 2. We like pi over 4. X coordinate is also root 2 over 2. Anything divided by itself is 1. Happy face. That's going to make this substitution process a little less scary. Yeah? I'm going to go back to my original question, which is what is tan of pi over 3 minus pi over 4? We have a fraction for that. It's tan pi over 3, which is root 3, minus tangent of pi over 4, which is 1. Denominator is 1 plus tangent pi over 3, tangent pi over 4. Tangent pi over 3 is root 3. Tangent pi over 4 is 1. Yeah? Okay. Perfect. So we get on the numerator, root 3 minus 1. In the denominator, I have 1 plus, and then anything times 1 is itself. So this is just 1 plus root 3. Am I done? Probably not, otherwise I wouldn't be asking that question. As a rule, mathematicians don't want to see fractions inside of fractions. That makes us unhappy. We don't want to see radicals in the denominator. That makes me unhappy. So I need a way to get rid of the radical in the denominator. whatever I do, I have to do it to both the top and the bottom, because I can't change the fraction. Changing my answer by slapping something new in there is cheating. If I multiply by the same on top and bottom, that's just multiplying by 1. That's okay. And I'm going to use the fact that I know that A plus B, come on, pen, there we go, times A minus B, that's a special factoring pattern. That comes from a difference of squares. A squared minus B squared is A plus B, A minus B. One of the first factoring patterns you learn in Math 2. Yeah? X squared minus 9. X plus 3, X minus 3. Right? X squared minus 49. X plus 7, X minus 7. X squared minus 100. X plus 10, X minus 10. Yeah? We're doing the backwards. We're doing the reverse. I want this is my answer, so I'm going to force this pattern to show up in my problem. If there's a plus here, I'm going to multiply by his minus buddy. There's a minus here, I'm going to multiply by his plus buddy. Same two terms, change the operation in the middle. Yeah? So this is 1 and root 3. So 1 and root 3 on top and bottom. Originally in the denominator it was plus, so I'm going to multiply by the difference instead. Because now I have a difference of squares in the bottom. That makes me happy mathematically. So let's start with the denominator, the easy part. Yeah? In the denominator, I know that this should be first term squared minus last term squared. So 1 squared is 1. Yes. Minus, what is the square root of 3 squared? Square root of 3 squared. What is this? 3, yeah. Squares undo square roots. So if I have square root of 3 times square root of 3, that's square root of 3 squared, which is just 3. Which is why we did this. If I multiply the denominator by the same two terms but with the opposite sign, I'm going to end up with these guys getting rid of that square root, and I don't get any cross terms because the outside is positive, inside is negative, or vice versa, and those middle terms cancel. I only get nice, pretty whole numbers with no square roots in the middle. The numerator is not so nice. The numerator is a binomial times a binomial. How do we do that? Distribute using one of two methods. We can FOIL. If you can FOIL in your head, that's the way I do it. Or the box method. One binomial along the top, one along the side, multiply to get each box. Yeah? I'm going to do first, outer, inner, last. So first is root 3 times 1, which is root 3. Perfect. Next is outer, which is root 3 times negative root 3. I know positive and negative is negative. Root 3 times root 3 is 3. We just did that off to the side. Now I'm going to do the inner, which is negative 1 times 1, which is minus 1. And then I do the last. So the last is going to be negative 1 times negative square root of 3. Negative, negative becomes positive. And 1 times root 3 is root 3. Group like terms and simplify. Group like terms and simplify. Stuff we know how to do, yeah? So in the numerator, we have two pairs of like terms. We have radicals, a root 3 plus a root 3, that's two root 3's. I have a minus 3 minus 1, which I'm pretty sure is a total of minus 4. I dig myself 3 feet hole, I dig another foot, I'm down 4 feet now, sad face. Denominator 1 minus 3 is minus 2. We can make that a little bit prettier. No, neither of them have come back yet. You have to wait. Let's divide top and bottom by the denominator. Let's split that up into two separate fractions and divide. So top and bottom, first pair, 2 root 2 divided by negative 2. Positive divided by negative is positive or negative? Negative, good. Different signs give me a negative. And the 2's should cancel. 2 and 2, leaving me with a root 3, which is a happy face. Second pair of terms, negative 2, negative 4. Negative divided by a negative is positive. 4 divided by 2 is 2. And you can write it in that order. More commonly, you will see mathematicians write the non-radical term first and the radical term second. Either of those answers is correct and fully reduced. Raise your hand if you thought that was gross. I thought that was gross. There is nothing in that process that is new. We learned about difference of squares in Math 2. We learned about fraction math in Math 2 and Math 3. You've seen radicals before in Math 2 and Math 3. You've seen rationalization before. None of those things are new, but you're used to doing them separately. Now we're doing a whole bunch of gross things all in a row, which makes it look scary, yeah? Do not be afraid to take this slow, one step at a time. Notice that I wrote out all of the baby steps. Yeah, I used multiple different colors. I actually did the tangent math, not in my head, but I wrote it out in red and blue. Yeah, and I color coded which angle was which. And you can color code the fraction all the way down if that helps you keep track. Yeah. This is not the time to squish 10 problems on a half sheet of paper and try and conserve a tree, yeah? Write it out, it will help. I'd like to do like 2 more examples. What do you mean no? You don't want to do more examples? You just want to take a quiz on Monday and have me assume you got it correct? Well, you got to do one or the other. If you're not ready for a quiz, that means we need more examples. There's graph paper up front if you need more. Let's do another example. No, gosh darn it. Only this class. Only this class. All right, we're going to do tan of 3 pi over 4 plus pi over 6 for funsies. I want to find the exact value, that's telling me no calculator math, Exact value of tan 3 pi over 4 plus pi over 6. Which brave soul can tell me what I should do first? That table that was confident they didn't need a second example is awfully quiet now. What do I do first? What did we do first in the last example? Plug it into the formula. Gold star for Yaya. I agree. This is the sum formula. I'm going to use the sum formula for tangent. Huh? I know the sum formula for tangent has the same operation in top plus opposite operation in the denominator minus. I know in the top it's tan plus tan. So tan of 3 pi over 4 plus tan of pi over 6. In the bottom, it's 1 minus, and then those two things multiplied together. Tan 3 pi over 4 times tan pi over 6. On your test, am I going to expect you have that memorized? Heck no. It would be on an equation sheet. You just have to know how to use it and take those two angles and shove them in where they go. Yeah, first angle's A, second angle's B, shove them in the formula. You guys can do that. What comes next? Juliana, what comes next? You're not sure. Check the last example. What do we do after we set the formula up? Frowny face. The answer will be the same whether you check it now or in 15 minutes. Sam, what did we do next? Good. So unit circle. I like you waving the unit circle. Perfect. Grab a unit circle, find those individual tangents. Perfect. So we grab our unit circle and we put it somewhere it's not blocking our handwriting. And we circle our two angles, figure out the tangent. So 3 pi over 4 is right here. Pi over 6 is right here. We're going to do that tangent math real quick. Yeah? We start with tan of 3 pi over 4. We remember that that fraction should be y over x, sine over cos. So the y coordinate is positive root 2 over 2. The denominator, the x coordinate, is negative root 2 over 2. Positive divided by a negative gives me a negative. Anything divided by itself is 1. Perfect. Negative 1. We like the quarter angles. Pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. Those are the plus and minus 1s for tangent. Those are where the sine and cos have that same absolute value. All right, next one, tan pi over 6. So looking at the blue, the y-coordinate is 1/2. The x-coordinate is root 3 over 2. That's less easy to simplify. So I'm going to use the reciprocal trick. Keep the first fraction, 1/2. Multiply by the reciprocal of the second, 2 over root 3. 2's cancel. I get 1 over root 3. As a mathematician, that makes me cry. I do not want root 3 in the bottom. So I am going to multiply the top and bottom by root 3. I want to get rid of the radicals in the denominator. In the numerator, 1 times root 3 is root 3. In the denominator, root 3 times root 3 is root 3 squared, which is 3. Happy face. So the first tangent's -1, second tangent, √3/3. Now that I know that, what do I do with those numbers? Daniel, what do I do with those numbers now that I know those? What do I do? Where do I go? What did we do in the last example after we figured out the red and the blue? Plug them in. Make a substitution. Everywhere I see a tan 3 pi over 4, I'm going to replace it with -1. Everywhere I see a tan pi over 6, I'm replacing it with √3/3. Perfect. So to scoot this up, I now know tan 3 pi over 4 plus pi over 6 is equal to tan 3 pi over 4, -1, plus tan pi over 6 is √3/3. The denominator of that formula, I have 1 minus, and then I have tan 3 pi over 4 times tan pi over 6. So tan 3 pi over 4 is -1. Tan pi over 6 is √3/3. Ugh. Gross. Icky gross. So let's simplify really quick. -1 plus √3/3. In the bottom, I have 1, and then I have minus, which becomes plus, and 1 times √3/3 is just √3/3. This fraction has two separate problems that make me very unhappy as a math nerd. There are fractions inside of fractions that make me sad. There is a radical in the denominator of a fraction. That makes me sad. I gotta fix both. My recommendation when you have both problems is deal with the fractions inside of fractions first. Once you've gotten rid of those nested fractions, dealing with rationalizing is easier. If I want to get rid of fractions, the fastest way to do it is multiply by the denominator, because then the denominators will cancel. So I'm going to take both the numerator and denominator, and I'm going to multiply by 3. Because 3 is the denominator of those nested fractions. This 3 is going to cancel that 3. This 3 is going to cancel that 3. There is a problem that you have to remember. Fraction bars are grouping symbols. This is a unit. We treat it like a binomial. Those things go together. This is a unit. We treat it as a unit. Those things go together. When I take a binomial and I multiply it by a number, that thing gets distributed to both terms. This thing gets distributed to both terms. A lot of students get so excited that they canceled the 3 in the second fraction, they forgot to distribute it to the first term too. You got to distribute. So let's take a look at what that looks like. -1 times 3 is -3. Happy face. And then a plus. And in that second term, when I multiply √3/3 by 3, the 3's cancel, and I get the numerator. Yay! Similar thing's going to happen on the bottom. 3 times 1 is 3, plus √3/3 times 3 is just √3. I have 3/3. I have one whole thing. In this case, the one whole thing is the radical 3. Closer. I still have one problem. There is still a radical in my denominator. Alexis, how do I get rid of the radical in the denominator? Okay, multiplying it by, what am I multiplying by?
Square root of 3.
Just square root of 3? Check the last example. No, not just a square root of 3, because then I'd pick up a square root of 3 on the whole number term. I don't want that. So the rule, take the two terms in the denominator, 3 root 3, change the operation between them. Right now it's a plus. I'm going to multiply by his minus buddy. And whatever I do to the bottom of a fraction, I have to do to the top. Otherwise, I change it. And we're going to see the same thing we saw last time. The denominators, that's a difference of squares pattern. That's a squared minus b squared. The numerator, we have to FOIL it out. So way back to like math 2 math. We'll start with the denominator. Difference of squares is first term squared. 3 squared is 9. Minus second term squared, root 3 squared is 3. Yes, that's the whole point. We got rid of the radical. Yay. Nice, pretty whole numbers. We know how to subtract. That makes us happy. On the top, remember that this is a binomial times a binomial. That's not a difference of squares pattern because of that negative sign here. So I got to FOIL this bad boy out. So first term times first term, 3 times negative 3 is negative 9. Outer, negative 3, negative root 3 becomes positive 3 root 3. I'm going to need more room here. Inner, these two guys, positive root 3, positive 3 is positive 3 root 3. Last is positive root 3 times negative root 3. So negative root 3 squared is 3. Yeah. Pretty sure that's loud enough to get recorded by the mic, so good job. Now it's just grouping like terms, making it pretty, yeah? All right, numerator, whole numbers first, minus 9 minus 3. I heard somebody mumble, it is minus 12, yes? 3 root 3 plus 3 root 3. That makes 6 root 3s. And the denominator, 9 minus 3, assuming I can do math in my head, is 6. And if I look at that fraction, the two whole numbers in the numerator are both divisible by 6. So let's carry out that division. Negative 12 divided by 6 is negative 2. 6 root 3 divided by 6 is root 3. That was an unhappy look, Aurelia. Are we okay? Okay. So reminders. When you do sine and cos, you shouldn't have that issue, right? You shouldn't have nested fractions. You might have to rationalize by multiplying by a root 2 or a root 3, but you shouldn't have to do this ugliness because those formulas don't have fractions built in. Tangent, you need to go through the whole process and reduce your answer all the way down to simplest form. No fractions within fractions, no radicals in denominators. Make sure the numerator and denominator are fully reduced. Yeah? If you are struggling in delta math with the tangent ones, it's probably you've got a fraction and a fraction, you have a radical in the denominator, or your numerator and denominator are not fully reduced, meaning they're both still divisible by a common number. Yeah. It is important you do the delta math, because you are not going to get better at this by listening to me yap at you. The only way to get better at something is to practice. That's why I wore my practice hoodie today. Yeah. So please make sure you do the delta math. Have some scratch paper out so you can do the math on paper. I am going to be around after school a little bit today. Not too long because it's Friday and I want to go home like you do. I will be available via email all weekend. I will be here Monday morning, Monday at lunch, Monday after school for math help. Yes? Yay.